All right, well, welcome everyone again, Harold said. And so let's get into the topic. So basically what this is. Let's start with the problem, because TFO is a solution, but before you discuss the solution, you have to first discuss the problem. What is the problem it's trying to solve? So consider the fact that the outside, you run a GSM network. I mean, I run a GSM network here in San Diego. Somebody else could run a GSM network somewhere else. But, running an isolated network is not really all that interesting. Typically, you'd want your network to be interconnected with the outside world. So you can call anyone in the world, anyone in the world can call you. So you basically will be interconnected with the PSTN, with the public switch telephone network. And I'm using that term in in its most general sense. PSTN to me does not mean copper wires. To me, PSTN means just public phone network in general. And so when you have that type of interconnection, then there becomes an issue that basically the outside PSTN works in G.711. It does not work in GSM codecs. So in GSM, we have all these compressed speech codecs. We have the old codecs that are just for GSM. You have the full rate, full rate, half rate. Then there is AMR, which is newer, and AMR is defined for more than just GSM. It also exists in TG. You can do AMR over VoLTE. You can do AMR in other contexts. But still, all of these are compressed speech codecs. Whereas the traditional phone network operates with uncompressed speech. In a traditional phone network, you just have a 64 kilobit per second channel, 8,000 samples per second, 8 bits per sample, with either A-LOR or mu-LOR encoding. That's what you have in the PSTN world. And so at the edge where your GSM network connects to the outside world, you're going to have a box called a transcoder, whether it be a physical hardware box or just software, it doesn't matter. It's a network element that does transcoding. And so, but the problem is that once you have crossed the boundary, once the call has left your network and gone out to the outside world, you have transcoded to G.711. So at this point, it basically becomes too late to apply any kind of Tandem-Free. Because basically now, let's say if there is another GSM network somewhere else in the world, right? So Alice on operator A calls Bob on operator B. And the connection between the two operators passes through the public phone network, passes through PSTN. So, Alice and Bob are both GSM users, and each network applies its own transcoder. So now you got a situation where you have a double transcoding going on. So you have speech being encoded in Alice's phone, then it is being decoded by the local transcoder, passes across PSTN, then on the other end, Bob's operator their transcoder will re-encode the speech, and then it will be sent to Bob's phone. But all these codecs are lossy. They're all lossy codecs. And furthermore, with all of these lossy codecs, if you pass through the codec twice rather than once, your voice quality degrades. In fact, the more times you pass through the lossy codec, the more it degrades. So there's no limit to how badly it can degrade. If you just keep going through multiple rounds of transcoding, you're just going to make it worse and worse and worse and worse. But even 2 rounds of transcoding, when people people who wrote the GSM specs back in the 90s, they also felt that even having double transcoding was already a waste, something that you didn't want to do. But how do you get around the fact that the middle of the network, the PSTN, can only pass 64 kilobit per second voice and nothing else? How do you get around that? And so they came up with this in-band protocol. So they came up with a solution where you have an in-band protocol inside the PCM sample stream. So that's what I call a masterful feat that they did. So that's really what this is about. So now let's see how all of this works. So another thing that's really important to keep straight, and the reason I point this out is there have been mistakes in Osmocom documentation. There are places in Osmocom code base in the comments where someone would say TFO when they really mean TRFO. So let's keep them straight. So TFO was the original acronym, and then when they wanted to make it transcoder free, they added the R here. So here is the distinction. So with traditional TFO, it's all in band. So you cannot meaningfully talk about TFO if you're not transcoding. So only if you transcode to G.711, then you can in band you can have TFO. But what we have in Osmocom, however, is different. What we have in mainline Osmocom, at least, is a TRFO. So what you have in TrFO is there is no transcoder at all. You just have compressed speech from Alice's call leg going directly to Bob's call leg, and there's really no there's no transcoder at all that it's passing through, and so this is what's happening in Osmocom. Except to make things even more difficult, is we're in Osmocom, we're doing a kind of informal TRFO, which is not quite the way 3GPP defined it. So in 3GPP world, the way they defined it, they wrote specs for TRFO only for 3G. So TFO, 3GPP specs for actual 3G, yeah, they came up with all of this out. This stands for out of band transcoder control. I haven't really studied it in detail. And then they have this BICC, bearer independent control product, bearer independent call control, which is what they had before they went to SIP-I. So they have all these things, but all of that, all of those specs, I mean, I haven't read those specs in great detail, but the little bit that I did read of the specs, they very coyly avoid mentioning of how it will work with 2G. So, which is really kind of dishonest in my opinion, because when ETSI passed the stewardships of GSM specs over to 3GPP, it was done with the understanding, at least that's how I understand it, the understanding was that they would not only develop 3G, but also serve as good custodians of what ETSI created for 2G, for GSM. And in many cases, 3GPP did an okay job on that. But in other cases, they just threw GSM under the bus. And a lot of the specs for things like TRFO, they literally threw GSM under the bus. They wrote everything up for 3G and GSM. Oh, you're on your own. Um, so, um, but in Osmocom, again, I'm not familiar with how Osmocom does 3G voice at all. I'm only familiar with 2G. But in Osmocom 2G, we're essentially doing informal TRFO in a kind that does not exist in 3GPP specs. And here I point out it can't exist in TDM. In TDM, it's impossible to do TRFO because in the original TDM-based architecture of GSM, you pass through the TRAU before you hit the switch fabric of the MSC. So even if the TRAU is co-located with the MSC, you're going to pass through the TRAU before you hit the switch fabric. So in that world, in the world of TDM-based GSM, you would apply in-band TFO even between two users on the same operator. You could have Alice and Bob standing on the opposite sides, of the same school campus, served by a single BTS, so that both legs of the call are on the same BTS, and they would be using in-band TFO to get the two TRAUs to negotiate and agree to be tandem-free, because that's how dark network works. But since we're not running TDM-based anymore in an IP-based GSM network, now you really have to deal with TFO only when we go to the outside world. We want to be tandem-free from one operator to a different operator. That's when it becomes interesting. So let's see. Yeah. This is another very unfortunate aspect about this. Like Harald was mentioning about the obscurity of TFO, is when I got into it, I read all the 3GPP specs. Great fun, but where are the practical implementations? So that was kind of my stumbling block. Like, well, where are the implementations? And and we'll cover later that there's really TFO has to be treated separately. There's TFO for the old codecs and there's TFO for AMR, and we'll see later in the presentation why I have to treat them separately. But yeah, finding a practical implementation of TFO was very, very difficult. Like I write here, I was not able to get TFO out of the local commercial GSM operators that we have around here. And I did get this TRAU. I did get this Nokia TCSM2 TRAU. There were presentations on the Retronet call covering it in detail. And that one works. That TRAU supports DFO for the classic codecs. So now we can actually test this. We can test classic TFO exactly how it works. But for AMR, see, this is the weird thing with AMR. So it supports AMR codec itself, but it seems like they don't support TFO for AMR. And I say seems because it's really difficult to even test. But I mean, look at what the docs say. If Nokia's documentation for the later version says this, then it's kind of discouraging me from doing all the extensive effort that would be required to even test for TFO with AMR. So, but we'll see further down what are possible approaches. So let's look at how this stuff evolved over time. So R98 was the first release where TFO was introduced. So all three of these classic codecs, were already present by the time of R98. They were all well established. Everything else was set up, but this is the first time we had TFO. So in the previous releases, R96, R97, you would have these codecs, but no TFO. So with those early releases, you'd be doing double transcoding or tandem transcoding, even with two users on the same BTS. Two students in the same high school talking on a phone, whatever. But yeah, so they introduced TFO here. They also introduced AMR in R98, but not for TFO. And same deal with R99. So in R99, again, no possibility of TFO for AMR. So with both releases, with both R98 and R99, you can do the older codecs with TFO, or you can do AMR without TFO. So pick your poison. You want a newer codecs? Give up Tandem-Free operation. So yeah, that really, TGP did not do well on that one, I would say. And then finally, in release 4, finally they introduced TFO for AMR. So yeah, they changed the spec. So it used to be 08.62, then it became 28.062. The spec totally restructured. The sections all moved around, doesn't look the same, and it is insanely complex. And for 3G, yeah. So at the same time, when for release 4, they introduced TFO for AMR, and for 3G, which is always AMR. And well, like I say, let's cover in the forward chronological order. So let's see what we've got here. Yeah. So this is a diagram straight from the spec, from the original spec. when it was all GSM. Yeah, this is one of those later 3GPP specs where they drew really pretty diagrams. So you can see here the mobile station, you can see the BTS, you can see the TRAU, and see so this is a transit network in between. So IPE stands for in-path equipment, because they realized back then already that when you pass through the public switch telephone network going around the world, it may not be digitally transparent. There could be all kinds of weird stuff going on in the intervening network. And of course, a lot of the things that can be going on in the middle can break TFO. So say if there's a segment somewhere that's purely analog, where let's say digital comes out here, let's say this digital go to pass through a DAC, and you have an analog leg, and then you get an ADC to go back to digital here. Well, and then forget about it. TFO cannot possibly work. But there are certain other types of IPE where they thought that they could make them support TFO if they would make IPE TFO aware. So the spec actually tells you how to design the IPE, the in-path equipment in such a way that it can detect TFO negotiation and pass the traffic through. So, for example, if the IPE is for an international connection or some other long distance connection where you want to save bandwidth, and they apply in one of the compressed, PSTN compressed codecs, like G.726 or whatever it's called, ADPCM, then of course it will not be digitally transparent to 64 kbps, but there's plenty enough bandwidth there to pass through GSM compressed speech. So if the circuit, what they call the circuit multiplication equipment that does the compression of 64 kbps into, say, a 32 kbps or 16 kbps link, if that equipment is made TFO aware, if it detects the TFO signaling, then it could pass through the compressed GSM speech and still achieve tandem-free operation. So the spec tells you how to do all of these things. But aside from the IPE, just in general principle, what you see is the decoder is always running. So in each TRAU, even when you've established tandem-free operation, you still have to run the decoder algorithm. You cannot disable the decoder because the upper bits, as we'll see, the upper bits of each PCM sample are still being passed through. It's only the least significant bits that are being replaced with the frames. So this plus symbol here shows how the TFO path basically mixes into the PCM sample stream. But then on the other end, you have a switch. You have this switch being thrown here. So when TFO is activated, the switch throws from this position to this position. And now this encoder can be fully disabled. And for each codec, especially for the later ones, like EFR and half rate, AMR, with all those codecs, the encoder is much more computationally intensive than the decoder. So if you can disable this, you can at least save some CPU cycles or DSP cycles. And then, and you can see the oval that depicts the TRAU is the biggest oval in the entire diagram, because they show this is where all the complexity is. So the beautiful thing about the original TFO design for the classic codecs is it's entirely contained in the TRAU. There was no need to modify any of the network elements. So the phones, of course, unmodified. BTS, completely unmodified. BSC, unmodified. MSC, unmodified. Now, you see there is this arrow. This arrow is dotted, the arrow between the TFO protocol and BSC. There is an optional provision to make BSC TFO aware for optimization functions for codec switching. So in other words, if this leg is EFR and this leg is plain FR, well, then it's a codec mismatch. They can't do TFO. But if you implement this optional arrow here, then this entity can tell the BSC, hey, the guy over there, Bob, his phone can only do plain FR, can't do EFR. Can you please switch the codec? And the BSC can switch the codec, and now you have a Tandem-Free operation. But that's optional. And the TRAU that I have here in the lab, Nokia TCSM2, it does not implement this arrow. There is no communication path from the TRAU to the BSC to this kind of codec switching business. But that's really the diagram. This diagram shows what TFO is all about. So now let's see in details. So here, basically, most of what was in the diagram I cover here. But this is in more detail. So prior to TFO establishment, because you don't know, when you first initiate a call, you have no idea if the party on the other end of the call is another GSM phone. Far more likely than not, it's not another GSM phone. Far more likely than not, it's a landline or office VoIP system or some other modern phone that refuses to modern phone system, VoLTE, whatever, that refuses to speak TFO. So most of the time, you're not going to get a successful TFO negotiation. So the idea is to reduce the amount of artifacts you introduce into the audio. And so what they do is that only every 16th sample. So every 16th PCM sample, you steal just one LSB, just a least significant bit. And that's how you transmit the in-band message, the in-band TFO request. And by the spec, it repeats the message 35 times, which works out to be about 5 seconds. So after about 5 seconds, it will give up and just go back to normal call operation. But if there is a response, then there is a negotiation protocol. And so that's how they figure out are they both GSM, do they both use the same codec, and also the digital transparency is tested. So like I said, there can be all these in-path equipments that make the path non-transparent. And it can also be worse. What if you've got a path that's transparent one way, but not transparent the other way? And so the protocol has to be aware of that so it doesn't get into false TFO when it shouldn't. But once it's established, then the switch is thrown. The switch that was in that diagram, we just saw that switch. And once that switch is thrown, now instead of stealing just one significant bit every 16th sample, now you're going every sample. So with half rate, you're stealing one LSB every sample. So you only got 56 kilobits left for actual PCM voice. With full rate codecs, you are stealing truly significant bits of every sample. Again, to make a 16. So at this point now you have a 16 kilobit per second subchannel that carries compressed speech tandem-free. And then the upper bits of the same PCM samples now reduced to just 48 kilobits per second. There you still have your traditional PCM voice. So anyone doing what they call lawful intercept and so on, they just wiretap the PCM channel. They will still pick up the speech in the upper bits of the PCM samples. And also, if there is some glitch happens and TFO breaks abruptly, it will take a little. The protocol responds pretty fast to those, but still, it's a finite non-zero response time for the protocol to detect breakage. And in that case, the person on the other end will hear somewhat corrupted speech, but hopefully still intelligible because the upper 6 bits of each PCM sample are still the decoded speech. So, and here I pointed out this paragraph, that's the reason why you are not allowed to turn off the decoder. So the decoder algorithm still has to be running. You still have to burn CPU cycles doing the decoder, but at least it's not the encoder, so it's less CPU intensive. And now we get to the really fun part. So what exactly do we put in those least significant bits when we steal them? And they are TRAU uplink frames. So this is the fun part. So you've got, now just to see how much fun it is, we'll go to the next slide. And now you can see just how fun it is. because I'm not going to read this whole wall of text. You can read it later. But essentially, the key takeaway is TFO causes you to expose a little bit of your network insides. So traditionally, you would think that, let's say, if you have an E1 based, TDM based GSM architecture, and you've got you have these TRAU frames there. You think that that's a private business, totally internal to your network that nobody on the outside can ever see, which normally is the case. But if you enable TFO, then it becomes visible to the outside world. I mean, I personally don't see any horrible privacy problem with that because, I mean, the content, the audio content of the call is exactly the same. It's not like, if anyone who taps the 64 kilobit channel in transit from one side to the other, it's not like they're gonna get some other secret audio that wasn't there otherwise, but they will see where. They'll see details about your network. They will see things like where time alignment happens. So in a traditional TDM-based GSM, on every 24th frame, aligned with the such structure, you have what's called a time alignment flag, which is necessary for the old-fashioned codecs. So that bit is included in a TRAU uplink frames, which will now be exposed to the outside world. You can also see when Alice's call lag experienced radio errors with BFIs, or they can see, like, say, if you have DTX and the uplink on Alice's call lag, anyone tapping the channel can see, was it at any given point in time, was it in speech mode or was it in DTX state? So these things become visible to the outside world. And so um, this was the point I made, how you have to treat the standardized protocols. It's almost like the public internet protocols, just like, the IETF, RFCs and whatnot. You have to start viewing it the same way because, you speak TFO, your TRAU UL frames transported inside TFO are now an interoperable interface, could even be internationally interoperable. So. And then the other thing, the last paragraph is really important. Now, take a look at this last paragraph while I take a sip of juice. So the important thing here is that this paragraph is very likely a contributor to why there are so few implementations of TFO out in the world these days. Is because if the network has migrated from the TDM-based architecture to IP-based transport with RTP, then it becomes really difficult to do TFO. And that's one of the reasons why I developed this at the Mosquito Wireless Technical Specification 001. Which is now supported in Osmo BTS and also in the libosmo ABIS for interfacing to E1 BTS. They all support this spec. Thank you to all the Osmocom reviewers who allowed it to go in. But I had to develop this because there was no other way to support TRAU, to support TRAU frames, transport, and TFO in an Osmocom-based network with RTP. Because if you use the standard, industry standard RTP payload formats, the same ones that 3GPP standardized for A over IP interface, well, they lose all this metadata. In that standard RTP format, there is no more time alignment flag. There are no more bad frames. All of that has been stripped out. So how would you go about converting that to something that looks like TRAU uplink frames in TFO? At least I couldn't find any clean way to do it, any way that I would be satisfied with. So, I decided to take matters into my own hands and create a non-standard spec for use inside the GSM network. But I'm guessing other network operators or other GSM equipment vendors were not as brave. They were not as willing to violate RTP specs in order to emulate ancient TDM more faithfully. So, just difference in values, difference in priorities. So let's see, where do we go? Yeah. So okay. So now we get into this part that's called what I call the TFO transform. Now this term TFO transform, that's a term that I created myself. I had to create my own term because there is no standard term. The spec, the TFO spec does not use a single short term, it's a short, concise term for this function. I mean, they describe what needs to be done, but they don't give it a specific name. So, but I thought the function is so important that it deserves its own name. So I called it the TFO transform. And we're going to see how important this transform, how it applies even to TrFO. We'll see in a moment. But consider this fundamental problem. So on a TRAU frame interface, the uplink frames and downlink frames look completely different. So the frames that pass across TFO, they look like TRAU uplink frames. They're very slightly modified. There's just a couple of bits changed, but other than that, all the semantics are the same, and most of the bits are the same too, just a few bits changed. And so now on both directions of the TFO call, you have TRAU uplink frames traveling, not downlink. But then the TRAU on each end has to take the uplink frames from the remote and turn them into downlink frames for the local. Well, and how do you do it? That's a really difficult problem because the uplink lag from BTSA, you can see here all the things that can happen there. But on a downlink, you can't have any of this. In a downlink, you have to have a perfect speech frame every 20 milliseconds without fail. You can't have anything else. So what do you do when you have all of these other things that can happen in the uplink? So you have to do what's called, the uplink to downlink transform or TFO transform. So yeah, and this is what the spec says. The spec uses the word shall. So by using the word shall, they're saying you have to do it. It's not an option. It's not something you can ignore. You have to do it. It's a shall. But then read this lovely language. Subject to manufacturer-dependent future improvements and is not part of this recommendation. I mean, isn't that lovely? They're saying shall, you have to do it, but they don't tell you how to do it. No algorithmic guidance whatsoever. And let's see here. And just to show you how difficult of a problem it is, how non-trivial it is. So also the difficulty of this problem depends on the code. So for the full rate, it's actually not that bad. For the full rate, because if you look at the full speech decoder, the regular decoder that takes the uplink frames, that takes the TRAU uplink frames and converts to decoded linear PCM and speech, it's already modular because they already have the RxTTX handler front end neatly separated. And so you can just take that neatly separated front end and you can turn it into a TFO transform. But even there I had questions, like here, the question mark here, I was just wondering, the historical TRAUs, do they really do it the simple way? Or like the reason I wondered about this comfort noise interpolation is if you read the spec, let's see which spec, this spec right here, 06.12, when it talks about comfort noise insertion, it uses this language. It says because every 480 milliseconds was when the parameter updates. So the comfort noise parameters update every 480 milliseconds, every 24 audio frames. And so when the comfort noise parameters change, the spec says user language should preferably be interpolated over frames. Notice, it does not say shall, it says should preferably. And I was thinking, well, do they do that in the historical trials? That was something I wanted to find out experimentally. And the answer is no, they don't. At least with the Nokia TRAU, the one that they reverse engineer, yeah, there is no interpolation, but we'll get to that. But at least, aside from the interpolation question, it's fairly simple. Now, when you get to the half rate codec, now it's getting a little bit more difficult. I mean, so one big difference between full rate and half rate is they now have bit exact fully, because full rate you only had bit exact for the core portion, but all these add-ons were not bit exact. Well, now it's bit exact everything. And if you look at the reference C source that they provide, it's partially modularized. It's almost a separate piece that you can separate from the decoder and use it as a TFO transform. Almost, not quite. And then you get the questions, because now the thing with the comfort noise parameters interpolation, with full rate, the spec says should preferably interpolate. For half rate and EFR, it says shall interpolate. So should preferably has changed to a shall when it comes to interpolation of comfort noise parameters. But that spec only applies to the regular decoder. In the case of TFO, they say, subject to manufacturer dependent future improvements, all that stuff. So the question becomes, well, when you do TFO transform, does it mean you have to take the interpolated CN parameters and then requantize them, or can you get away without it? Yeah, I had to find this was not clear. How do the historical trials do that? And then, with this UFI error flag, you can just watch my previous presentation on the half rate error flags. It's a mess. And now the EFR is the most difficult of all, because with the EFR codec, is you have the official reference decoder. It's bit exact. They give you a C code, but it is fully monolithic. There is no more separate receive DTX handler front end. All of this, stuff, all of this extra magic here, it all happens inside, right in the guts of the decoder, not separated in any way. So how do you factor it out into a TFO transform? Well, you can't factor it out. At this point, basically, you have to design the TFO transform from scratch, just from theory, from the theory of how codec works. Yeah, so, and all of these mysteries, ever since I read the spec, I had all these questions. And I was like, and how do I answer those questions? And that was that's what sent me on the quest to acquire a TRAU. So, in those previous RetroNet called presentations where I discovered all my escapades, reverse putting together the Nokia TRAU and getting it to work. So the reason why I had to go on that journey was to answer all these questions. So now let's see where else this takes us. So these are my findings from the Nokia TCSM2. So the TCSM2 is the name of the specific model of Nokia TRAU that I got. And there was another really trying movement is when I read in the manuals that it's a premium feature. So in other words, you might not get it. Now, I don't know. I mean, the TRCO is the transcoder controller. That's the main board in this TRAU. So I don't know if they made different main firmware builds for this TRCO or if it was some kind of license key scheme, but I didn't see any place in the admin interface where you would enter a license key. So I don't know how they did it. But like I said, thank heavens that the one I got came with this feature included, because otherwise it would have been trying to reverse engineer that 8186 firmware, because it's an 8186 based module, and try to figure out how to hack enable it. Yeah, thankfully it came included. But when the feature is present, then you have the admin interface. You go in the management interface, and there are commands that can enable or disable it. And the official networks, they would do it from the BSC, but I don't have a BSC, so I just use the RS-232 port. And again, thankfully, they allow the RS-232 port to be used to basically do everything that you would normally do from the BSC. And so once I did it, once I enabled it, thankfully, again, it behaves just like I would expect from reading the spec. Because, I had read the specs months, actually like a year or two before I finally got my hands on the TRAU. So at that point, I had I could pretty much recite the spec in my sleep. And I finally started playing with the TRAU. I was so delighted to see that it behaves exactly like would expect from the spec. So the channel has to be active from both sides. The channel comes to life when you have when you have the TRAU uplink frames coming in on the 8-tier interface, and here's it coming from the BSS. I mean, strictly speaking, coming from the 8-tier. So you have the uplink frames coming there. It detects from the TRAU UL frame type. It figures out what mode it needs to go into, which can be either speech or CSD. And if it's speech, which codec it is, it figures all that out automatically. And that's how the TRAU channel comes to life. But then in order for the TFO to come to life, it also, from the MSC side, has to be getting something other than the idle fill pattern. So when both of those conditions are met, then it starts emitting the TFO messages. And again, it does all of this 3 times the fill and then 35 times the request, exactly like the spec says. Yeah, this is how long it lasts. So after 5 seconds, it'll just go back to normal. And here is the fun part. So if I take 2 different E1 time slots on the A side, the 64 kbps side of the TRAU, and I should say of the TCSM, because a TRAU is each individual channel. So on the A side of the TCSM2, I cross-connect those 2 channels, and I get successful TFO. Yay! So the protocol, and this was another thing. So read the slides while I take a sip. But basically, one of the reasons why I was so interested in this is I want to implement this. This is a project for later, but it will happen. Maybe this year, we'll see. Maybe not, but maybe. And so most of the other infrastructure is already in place. So maybe soon. Idea is to eventually have free open source implementation of TFO protocol working with Osmocom-based GSM networks. But the problem with doing that, just working from the spec, it's so complex. It'd be so easy to make a mistake anywhere in a complex protocol and not even know you got it wrong. Okay, you can do unit tests. I mean, you can do what Osmocom mainline does with all of these TTCN3 and whatnot. But if it's one person doing it all, writing both the tests and the actual code, if the mistake was made at the point of interpreting the spec, you'll never know. So have to be able to test against implementation that's not your own. That's essential. And if those implementations are so rare, well, that's the problem. But thankfully, we can now study Nokia's implementation. So here, what I did was, because I didn't do my own implementation trying to interoperate with Nokia's, I just took Nokia's implementation. So I just took 2 channels and did this what I just said here about 2 time slots cross-connected. Mostly I only noticed one discrepancy between my reading of the spec and what the TRAU does. You can see it's a 1-bit difference. So I would say it's a bug. I mean, in Nokia's side, I really looked at the spec closely. I don't see how. I mean, the spec says the bit should be a 1. And they transmit 0. Oh, well, I mean, it just that means that in our implementation, we have to be aware that some people got that bit wrong. And we don't have to look at that bit because we can see the length of the message. So if the length of the message, and it tells us whether or not there's a codec list included, so you can just ignore the, this list indicator bit, we can just ignore. Um, Postel principle, be conservative, be liberal in what you send, but conservative, be liberal in what you accept and conservative in what you send. So we're going to be liberal in what we accept by allowing this bit to be wrong, but conservative in what we send, meaning that we will send it correctly, and hopefully it will interoperate with Nokia. We'll see. That remains to be tested. So let's see, where are we now? All right. So here we can see that once I got past those previous steps, once I got past the point where yes, it really does implement TFO, and yes, I can take two channels and cross bridge them together. Once I was able to get past that hurdle, then I could test the next step. Then I could test and see what happens with the transforms. So on one channel in the TRAU uplink frames, I can feed whatever test patterns I want, and then see what comes down in the TRAU downlink frames on the other channel. And that's how you can tell how the TRAU implements the elusive transform. And that was, these first two lines, the first paragraph, that's the biggest key takeaway, that they really do it the honest to God, no cheating. Because that was uncertain to me as well. The 3GPP spec uses that word shall in there, but there is also the reality that ABIS is not in reality an interoperable interface. I mean, TRAU frames are standardized, but because some aspects of OML and all that are not standardized, in reality, ABIS has become a de facto vendor-specific interface. So, given that reality, Nokia may have thought, hey, if we can't interoperate with anyone on ABIS anyway, why don't we just make our life simpler and cheat when it comes to this TFO transform? But no, they did not cheat. And so the cheat, an example of how would you cheat? Well, look at Osmo BTS. Specifically, look at my patches that got merged. When was that? 2023, I think. So there was a series of patches where if the RTP, because the RTP stream that comes into Osmo BTS is logically, conceptually equivalent to the TRAU UL frame stream in a TFO transform. So if the incoming RTP stream has gaps in it, or if it has DTX, and on the downlink you can't have DTX, well, what do you do? So the cheating tricks that we do in Osmo BTS are pretty simple. One, when it comes to DTX, separate logical DTX from physical DTX on the downlink. So on the downlink, if you can't have physical DTXD, well, do a logical, to where you transmit the seed frames just like as if you had physical DTXD, but instead of physically turning off the radio transmitter, you just put induced BFIs. And do the same thing if there's just a frame gap, whether it be packet loss or an actual BFI, you got a gap somewhere, well, transmit inverted CRC. So when we transmit inverted CRC on a downlink, by doing so, we induce a bad frame indication condition in the receiver on the mobile station side, and we can do it for both frame erasure gaps as well as to create fake logical DTXD in the absence of physical DTXD, same trick. And so, since we did this so easily in Osmo BTS, which works, by the way, not only does it work on the TRX base, it even works on the Sysmo BTS with the proprietary PHY. Because if you send the zero-length payload to the proprietary PHY, that's what it does, what I just described. So, yeah. So considering how easy it was to do that, I thought, well, maybe Nokia had the same idea, but no, they did not. They implemented what I call the honest-to-God TFO transform for all three codecs. Full rate, half rate, EFR, they do exactly what the spec says, the whole complex transform. Now, the algorithmic details of how they do it will be way beyond this presentation, but these are the detailed notes. So I'm going to post the PDF. I always post my slides, so you can later follow these links and you can read all these notes on exactly how they do the transform. And so, as well as the theory. So, of course, my eventual goal is to create published source implementations. Unfortunately, it's one of those things where, how do I say it? Published PSS, published source software, is in mathematical terms is a superset, whereas conventional FOSS is a subset of that superset. So because of ETSI's so far unwillingness to drop the stupid copyright claims on the half rate and EFR codec sources, my own Themyscira wireless codec libraries for half rate and for EFR PSS. So you can also call them IFS, illegally free software, but but at least, for the full rate codec, at least for that one, we can have a true proper FOSS, because that one was my own original work. So that one we already have. The latest release of the Themyscira GSM codec libraries and utilities package, it already has a working TFO transform for full rate. It's just the other two I'm missing for now. Which I need to implement, as inspired by these reverse engineering notes. And we'll have the difficulty of it being PSS and not FOSS. Oh well, what can we do? So moving on. So ARIA. So the significance for SMARCOM CNI. So, all right. So people on SMARCOM may think, okay, well, this is all just fun, retro networking, knowing how TRAUs do it and whatever. How does it matter for us? How does it matter for SMARCOM people, you may think, right? Well, with native OSMA BTS, we can cheat. And I already described the cheating. So as I was yapping before, how the cheating is done, very simple. But what if you have an E1-based BTS? So let's say you have an E1-based BTS, such as, the Nokia BTS. I have an insight here. Thanks, Harold. Thanks, Sarah. And which is good for experiments, but that's not exactly like production hardware. But then, considering how the availability of Ericsson RBS 6000 BTS hardware, that actually is professional grade, production suitable hardware, that's probably available for much, much cheaper than what it would cost to get newly made OSMA BTS TRX-based functional equivalent with those high power levels and everything. It really becomes kind of important to be able to support E1-based BTS. And here becomes the problem, is we need that same TFO transform, even if we don't actually do TFO, even if you don't have anyone in the world that you would ever care about doing in-band TFO with. If you're only doing OSMACOM style TRFO, even then you still need a transform, because the RTP stream, the TRFO style RTP stream as it exists in OSMACOM, is logically, conceptually equivalent to the TRAU uplink frame stream in TDM. So because in the RTP stream you have gaps, you have packet loss, which you should treat the same way as if it was BFI. You can have actual BFIs from call leg A. You can have, call leg A could have had patch stealing, and you got a frame gap for that reason. And also DTX. So let's say, you got very little spectrum. You only have enough spectrum to run a single ARFCN BTS. So if you only have carrier 0, you can't have DTX downlink, but you do want DTX and uplink to save power on the phones. You're back to the same problem of needing a TFO transform to deal with all of these things. And so, let's see what I wrote here. The way it is handled currently, actually, when I tested this with this little Nokia Inside BTS that I got thanks to Sarah and Harold, the result is that it works, it works kind of sort of with full rate, but not with EFR. So if I enable EFR, it immediately, with EFR, as soon as the incoming RTP stream has any kind of gap in it, the BTS immediately declares a remote transcoder failure, tears down the call. Because what happens in current Osmo MGW is it just has a dummy fill. So there's an extremely simple algorithm there. There's no transform, none of that. Just take whatever comes into RTP, it immediately feeds that to the TRAU downlink. And if nothing came in on RTP, if you got a gap, well, just be made a dummy filler. And dummy filler just happens to be valid for FR. I mean, it's not good, it's not correct, but at least it's valid enough to where the BTS does not tear down the call with a remote transcoder failure indication. But for EFR, it does tear down the call with remote transcoder failure indication. And it's not just, let's change this dummy filler to some other filler. Well, no, there is no constant filler to be correct. The only correct solution is to do the transform. So, which is basically a problem, and it's a problem for the same reason as to why I just discussed the whole issue with the distinction between traditional free open source software versus published source software, is that in my case, I really want EFR. I really, really, really want EFR. But for EFR, the transform will most likely involve taking some bits and pieces from the original Etsy code base. So, and that's why there are all these problems now. It can be brought into Osmocom mainline and all the problems happen with that. So, one of my many projects on the back burner, I have my own replacement for Osmo MGW in the role of E1 ABIS. So Osmo MGW is really the way I look at it. It's two entirely separate functions that are just spliced into the same process. So there is the function of the RTP bridge, which forwards from one RTP leg to the other without introducing any artificial delays. That's good, not so fine and dandy. And then there is the completely different function of interfacing to an E1 ABIS. So for the E1 ABIS interface role, I just started up. It's not finished, so you can see it in Git here. So I have the beginnings of TW E1 ABIS MGW, which is basically the new media gateway for talking to E1 ABIS, and it makes use of the ThemY RTP library, the same one that's currently in Gerrit and trying to get into the Bosmania TF. But it also absolutely critically depends on Themyscira codec libraries, which is a problem for those who require a solution that satisfies traditional FOSS definition. Now, thankfully, if you don't care about the EFR, if you can live without EFR, and if you can live without half rate, if you're happy with just full rate speech plus CSD, that one should satisfy the traditional FOSS definition, because the only codec library you need from the Themyscira realm is the one for full rate, which is my original work, therefore does not have any copyright problems. But if you want the other codecs, then it's a problem. But in any case, this is still, it's a very, very unfinished work in progress. I had to switch to other priorities, so it's kind of left unfinished for now. I don't know when I'm going to come back to it eventually. So, but that basically shows why it's important to have the transform even in Osmocom world, even if you're doing TrFO and not TFO. So, all right. So now we can we are past the realm of full rate, half rate EFR, and now we can look at AMR. So AMR is really just an entirely different animal. TFO for AMR does not look anything like TFO for the classic codecs. Plus, of course, the historical gap in the definition. So, like I said, the TFO, this kind of TFO was defined in R98. So R98, they defined it, has not changed since then. TFO for AMR only came into being starting with release 4, and it came into being for both 2G and 3G at the same time. So let's just see how difficult it is, or how different it is from the traditional. So first of all, it's no longer confined to the TRAU. So the traditional kind, it's all in the TRAU. The other network elements don't even have to know about it. Nope, not here. And look what they did, several different ways. So you can read the spec, and the spec literally presents several different alternatives, how you can take the logic of TFO and split it between these three guys, TRAU, BTS, BSC. At the minimum, BSC has to be, at the minimum, BTS has to be involved. So I think the BSC is still optional. It's still possible for the BSC to not be involved, although there are some options that require BSC involvement. But at least at the minimum, the BTS has to be aware of TFO. It's no longer just a TRAU thing. And also because they offered so many different ways, and again, that just raises the question. So if anyone did implement this, I will drive it one more nail in the coffin of interoperable ABIS, because they each did it their own way, with the spec giving them explicit permission to choose one of several different ways. So, but at least on the 64K side, it is still intended to be globally interoperable. You can still have, transcoder on one end of the world talking to another transcoder on the other end of the world across the global PSTN. And it's supposed to be interoperable between full rate and half rate AMR and between 2G and 3G. It's all supposed to be globally interoperable. But the price is the complexity, and it is through the roof. So let's see. Let's look at some of the complexity here. So now when they do the in-band message exchange, with the simpler codecs, they just say, okay, I'm doing full rate, I'm doing enhanced full rate, whatever. But now they have to exchange information about active codec set, supportive codec set, and what are their capabilities in terms of changing. Now, also, I don't know if they still do that. I don't know how commercial networks really do it. I've never been an AMR person. But apparently, at the time when the specs were written, they would expect, because when you configure AMR, you have a total of 8 modes, and you choose which 4 modes out of the 8 you're actually going to deploy on your network. And they expect that this choice is going to be different for different cells, because apparently the choice that's good for urban cells is different from rural cells. I don't know, not an expert in that by any means, but that's what the spec says. So supposedly, and now if you've got such changes on one side, they affect the remote side, and so that's why they really have to think about the ability for it to change, how it has the active codec set would also support the full 8 of supported, and then being able to change, to accommodate the TFO partner. You can just see the complexity going up with all of that. Then you have interoperability between full rate and half rate. So full rate, you have a 16 kbps TRAU frames. Half rate, you have 8 kbps TRAU frames. And now what if you have full rate on one end and half rate on the other end? So the spec requires the full rate end to adopt the half rate frame format in that interoperation scenario. And they also leave it as an option. Is the BTS switching the format, or is the TRAU converted on the fly? The spec allows both options. Again, complexity. And now, this part wasn't even in the spec, but if we were to do this in SMACOM, we'll have to deal with the extra complication that we use RTP. And now, I'm really not familiar with IUUP, really don't know much of anything about it, but it seems to me that RTP transporter AMR, someone correct me if I'm wrong, is a little bit closer to IUUP than it is to TRAU frames. Because if you look at the TRAU frame format for AMR 08.60 spec, it's very different from RTP. So I don't know. It seems to me that RTP is a little bit closer to IUUP, but I could be wrong. But at least the reason why I mentioned IUUP is the spec, the 28.062, it does support TG. So, they have an Annex C that covers TFO and GSM, and there's Annex D that covers TFO and 3G, and Annex D talks about IUUP, and it talks about converting frame formats, because in 3G you have IUUP on the red side, but inside the G.711 PCM sample stream, inside there you still have TRAU frames of 08.60, including the AMR version, including the AMR TRAU frames. So you have to convert them. And then you have the CMR CMI phase. So because in GSM you have alternating phase with codec mode request, codec mode indication. And if you look at the TRAU frame in a TRAU frame format, there is a bit. There's this RIF bit, the request indication bit, that goes 010101, telling you which of the two it is. But in RTP, that's not there. And from what I understand, IUP, it's also not there. And so they tell you how you have to recover it, how you have to look for when the codec mode changes and figure out, oh, if the codec mode changes, this must be a CMI frame. Oh, just complexity. And and so here, these are just some thoughts, the thoughts that I had so about how we might approach this. I read this while I. So, I went through quite a project to acquire a working TRAU that supports TFO for the classic codecs. But as far as I can tell, it does not support TFO with AMR. Now, here I explain why I am not going to try to find another TRAU that supports TFO with AMR, because it would be rather pointless without the BTS. Because how I really explained, in the case of TFO AMR, it's not just a TRAU. You have to have the TRAU and the BTS working together. And because the spec offers so many different options for how you can split the work between different network elements, you just don't know how each given vendor did it. And so, but I was thinking it would be better, it would make more sense to start from the BTS side. So instead of starting from the TRAU side, start from the BTS. So if someone has an E1 BTS with AMR, and I'm going to cover the RBS6K later. I have a later slide for the RBS6K. But I know, I guess I don't know, but I was told that Nokia inside does not support AMR, but the higher Nokias, the Metro side, supposedly those do support AMR. So if someone out there, watching this or later has an E1 BTS with AMR capability and you want to play, well, this is what I recommend. So you take this program. So this is the program that I have in my Git. It used to be Mercurial, but I've moved all this stuff to Git just to make it easier, harmonize better with osmocom. And so you take this program and you just extend it, you hack it up to emit something in a downlink. So just to keep the BTS happy. And you capture it, capture whatever the BTS puts out. The important thing is this, that the channel activate. That's the command you send from the BSC to bring up the channels. So in there, you have to include this multi-rate control information element, and that's where you set up, what your AMR modes and all of that. And I assume none of this has ever been tested in Osmo BSC with AMR and E1 BTS, so you'll be the first to test all of those things. But in there is a bit also that either enables or disables TFO. I think it's actually, they have it the sense in reverse. So if the bit is 0, then TFO is enabled. So I guess they want it to be enabled by default. I assume if they made 0 enabled and 1 disabled. But anyway, you have to set that bit, and then you have to see what the BTS puts out in TRAU uplink frames. Send me the capture, and if someone finds that a given E1 BTS supports not only AMR but also TFO AMR, then maybe we could do this part in software. These are just musings, really. So let's see, almost done. So yes, another very important question on the subject of E1 BTS. Again, someone please correct me if I'm mistaken here, but my understanding is that no one in osmocom so far has tried AMR with E1 BTS at all, not just TFO, but period. And even when someone tries to do it, there's going to be difficulties. So consider the fact that in SMARCOM we do TRFO. We don't do TFO, we are TRFO. But how are you going to force it onto the BTS? So as I was describing several slides ago, when we do it for the older codecs, FR, HR, AMR, we have to implement the TFO transform. We do the TFO transform, we treat the incoming RTP as if it was TFO uplink frames, and then we just synthesize the downlink frames from there. That's what we do with the older codecs. We cannot do the same thing with AMR because the TFO transform does not exist for AMR. It's not defined for AMR. For AMR, what the So what the spec officially says for AMR, because for AMR, they only support, 3G support officially defined TRFO only for 3G, but not for 2G. And in GSM world, you still officially 3GPP defined only TRAU frames. And so the officially per 3GPP, if you have an E1 BTS and you go into AMR, is you can only have two modes. You can either have modes with full transcoding, where the local TRAU or TRAU equivalent does full 100% transcoding, or you can have TFO, but no TRFO. And if you do TFO, then both the TRAU and the BTS has to be involved. So the BTS has to be involved with that. And when the BTS goes into TFO mode, then what happens is the uplink frames in the far end pass through the TRAU and into the BTS. And then the BTS, and notice this, that trick that I did with inverted CRC, it's a hack for the older codecs. But for AMR, the inverted CRC trick is official. And here is the chapter and verse. Here is the spec reference where they tell you how to do the inverted CRC trick for AMR. But it's officially blessed only for AMR and only officially by the spec. This section only applies when the BTS is doing TFO. So if the BTS is doing TFO with AMR, I should say. So if you have a BTS that's AMR capable and capable of TFO AMR, and it has negotiated TFO mode, then and only then is the BTS expected to do this trick where it will invert the CRC and do a few other things to make tandem-free or transcoder-free calls work. But that raises a question. If a given E1 BTS does not support TFO AMR, and I'm kind of getting the fear that they don't, well, what do we do then? Let's say we've got an E1 BTS, does not support TFO, does not support AMR. So in other words, when we send it the channel activate, we include the multi-rate control IE, telling it what the active codec set is and whatnot. But even though we say TFO enabled, which is zero means enabled, if it just ignores that bit and does nothing, does not do any TFO related logic, what do we do then? How would we feed TRFO to it? Well, that's an open question. We have to experiment and see what happens. We experiment with each given vendor model. So, like I said, we just don't know. We have experimentation. So, let's see. Almost done. So, now we got, this is a bit of a zoom out. So, okay, let's step away a little bit from the BTS. Let's step away from these details and look at the bigger picture of TFO AMR. Is there anyone in the world who implements it? So it doesn't have to be 2G. It could be 3G. Hypothetically, someone could even do it with the modern stuff, with Volte. If you got a Volte phone where your codec is AMR narrowband or even AMR wideband, there is nothing in theory that would prevent, because all of those, all those Volte not operators, let's say you got a modern Volte phone, you're doing AMR, like normally you do AMR wideband or whatever it is, but then you call someone who's on PSTN. So if the person you're calling is on PSTN, and PSTN only supports G.711, nothing else, then this modern Volte network still has to run a transcoder. So theoretically, that transcoder that they have to have, there's no reason why they couldn't implement TFO in there, except that it looks like they don't. At least in this country where I am, nobody implements it. So that's kind of the question is, anywhere on the scale, anywhere on the continuum, where on one end, if we draw TDM-based GSM networks on one end and modern VoLTE networks on the other end, and we have this whole continuum in between. Is there anyone anywhere along that continuum who implements any kind of TFO AMR that we can actually interoperate with across global PSTN? See, the reason why the question matters is, like I said, is there anyone out there to interoperate with? That's the question, because the protocol is super complex. I mean, even this one's already complex. This one's even more complex. So at least with this guy, what I write here in this paragraph, so at least with this guy, we have the TRAU, the Nokia TRAU. So even if there's nobody left in the world, no commercial operator left in the world with whom we could establish an international call across PSTN and have TFO, at least we could test our flaws, whatever, implementation for correctness by testing against the Nokia TRAU, and then we could have TFO between us, between one community GSM network and another community GSM network. We could have, and we could do it knowing that we did it correctly because we have interoperation with the Nokia TRAU. But how will we do the same for TFO AMR if there is no one to interoperate with, no way to test? Like, let's say if we try to implement it, if we try to implement TFO AMR protocol, how would we test the implementation for correctness if there is nobody to interoperate with, not 2G, not 3G, not anything? So that's a real big open question. And I believe this is my last slide. Yeah, this is my last slide. And so I'll take a sip. You can read the slide while I take another sip of juice. So this BTS is of most practical interest because, for obvious reasons, availability of the hardware and its, professional stuff. And, I have, this is the hardware that I have. This is, the date codes that are on the stickers. And this is why it was decommissioned. It even came with T-Mobile property stickers. And of course, considering how hostile T-Mobile is to 2G, how they're just itching to kill it, I think there would be a great sense of poetic justice in putting together a new GSM network that's made with decommissioned T-Mobile equipment. So, and here's the question about AMR. So I'm going to assume it supports AMR because look at the date. It was made around 2014. By that point, everybody was using AMR. So I would think that they would be using AMR. But again, in SMARCOM so far, nobody has ever done in SMARCOM E1 BTS with anything other than FR1. So I'll be in uncharted territory there. But again, I'm going to assume it supports AMR. But here's the question. Does it support TFO AMR? And somewhere, so I mentioned that it does not. Well, that raises the question. Let's assume it does not support, let's say it does not support TFO AMR. So it supports AMR, yes. TFO AMR, no. Let's assume that's the combination. That also raises the question. Okay, but all those big networks, so because they all did essentially TRFO, because when 3GPP standardized A over IP, I mean, I would imagine that most people, at least that's what I hear, from, people who use SMARCOM commercially, the SMARCOM community is commercial community is everybody is, so many people are using what is it? They're taking osmodevcall and connecting it to third-party commercial proprietary MSCs out there, and they all use 3GPP AOIP, and it just works. Well, that kind of tells me that everybody in the commercial world implemented the 3GPP AOIP with the compressed speech option because that's the only one supported by SMARCOM. And so, okay, well, if that's the case, if everybody out there in the industry on the A interface, if they're now passing RTP packets in a standard RFC 4867 format that's compatible with SMART-COM, if that's what they all do on the A interface, and if your ABIS interface that now the ABIS interface on RBS6K, I know they have their own IP transport. I know they have this Ericsson TFP traffic forwarding protocol, but when I read the spec, it looks like there is no change in semantics. So all the frame formats in Ericsson TFP, they have the same semantics as this, as 48.060. And so then they have to be, if they're doing what I think they're doing, what I reason here in this paragraph, they must be taking the RFC 4867 from the A over IP interface, and they have to be somehow converting it to TRAU downlink going to the BTS. The exact same function that we would have to implement in the SMART-COM if you want to get AMR working with this gear. And then how do they do it? Because that goes against so this is the big open question, and that's the end here. So yeah, I'm on my last slide. So now let's discussion time.
Well, first of all, thanks for the comprehensive presentation. Definitely some new thoughts and knowledge also for me. I mean, I can confirm that I'm not aware anyone having done AMR with E1 based BTSs with Osmocom software. The main reason is that, well, the let's say the high days of E1 based BTSs was with the BS11 back in the day, and the BS11 doesn't support AMR at all. It's too old for that, so that never was a chance to do it. And AMR was first encountered at a time when most of the development was using IP access nano BTSs and then Sysmo BTSs later on. So AMR with E1 wasn't on the agenda sort of until the RBS 6000 support came around, and it never was critical. I mean, it was sort of, yes, that's something we could do at some point, but it never was a high priority item, so it never got implemented. And regarding maybe a comment on the slide that you have here specifically, that you think they converted somehow. I guess they do, yes. I mean, this new transport for the TFP is only optional, by the way, right? It's only if you use the packet ABIS, how they call it.
Well, yes, it is true. Not only is it optional, but even when you do choose to use it, it does not change any of the semantics, because the semantics of what goes into the TFP is exactly the same as the good old 08.60. That's what I was trying to say.
Yeah. I mean, you have the classic ABIS with individual time slots and TRAU frames. You have the packet ABIS, and then you have packet ABIS over IP. These are the three basically options.
Well, yes, all of that is true, but you're talking at a low level. Think one level up. Think about the semantics of AMR.
No, I hear you.
Yeah,
thanks. No, it's fine. The semantics are the same, and I agree that in their let's say BSC co-located media gateway, they would have to do this translation that you're talking about.
Yeah. And the logic and how the translation would work, because I'm guessing that they probably applied a loose interpretation of the spec. So if you were to interpret the spec, 48.60 exactly like Dr. Water 3GPP says, and basically by the strict reading of the spec, you are not allowed to pass anything other than the output of a free running speech encoder, unless you're in TFO mode. So if you're not in TFO mode, it has to be free running speech encoder output, perfect speech frame every 20 milliseconds without fail, nothing else, no funny business, unless you switch into TFO. And if you switch into TFO, then you're allowed to send all these other possibilities. And the BTS has to support TFO negotiation. That's by the word of the spec. I'm wondering if Ericsson and perhaps others, if they maybe applied a loose interpretation to where they allowed all those other possibilities to be there, even though there is no TFO negotiation at the BTS aware level. I don't know, just a guess. To be determined experimentally, to be tested.
Yeah, I mean, I definitely don't have any other equipment than the Ericsson RBS 6000 Duke 10 20 that would support it. I mean, hypothetically, I still own a Nokia. What is it called? The Metro side, I think. I think it's a 4TRX unit that I haven't seen in probably 10 years, but it's with another guy in Berlin who wanted to play with it. Supposedly, I could get it back, but yeah.
But wasn't there someone in the community that's currently working? I can't pronounce the name. CSABA, something. CSABA. I can pronounce it.
Yeah, it's a Hungarian guy.
Okay.
He is with, or they are with a university there that has lots of legacy BTS equipment to play with. That's my understanding.
Okay. Yeah. I mean, if that person is actively playing with this stuff, it'll probably be a more accessible route and have a new dig up yours, or track down the person who you gave it to. So, but in any case, I'll probably be more interested in the Ericsson RBS 6K than the Nokia, because the RBS 6K is a more practical option, and I have the equipment right here. It's just there's only so much time, so I don't know when I get around to it, but eventually, maybe we'll see.
Yeah, I don't really have much other comments. I mean, I think you mentioned something about IUUP and that you didn't look at it in detail, but you thought it's more similar with, sorry, what was exactly the statement?
Okay, so what I was wondering is this. I was wondering because basically in a 3GPP world, in a world that's referenced in from the 28.062 spec, there are two transport formats that recognize as legitimate. So there is the 48.060 format, basically TRAU frames for AMR. And then in 3G world, they have IUUP. The third option, which is AMR in RTP following RFC 4867, which was later blessed by 48.103 spec, that option is not recognized as legitimate by 28.062. So, and I was just thinking, I was musing there, out of the two options which are recognized by 28.062, being either TRAU AMR frames of 08.60 or the IUUP for 3G, I thought that that RTP would be closer to IUUP than it is to the 48.060 format for AMR. That's what I was musing.
Most likely it is. But it's also not very much like RTP. So IUUP is a very strange format, and you have to look a bit at the history of how it came about. That the 3G was originally specified not using IP backhaul, but ATM, of course. So an original UMTS base station would have an inverse ATM multiplex doing ATM over 4 E1s. In ATM, they are using, I'm not sure which ATM adaptation layer. I guess it was AAL2 or something. But so basically, the voice channels would go into ATM originally. And then the RTP or the IP-based backhaul option for the IUB interface and IUV and IUR interfaces, that came only much later. And I mean, basically, they use RTP because sort of RTP is for transporting voice, but the IUUP spec says, well, please don't look at anything in the RTP header. So you shouldn't look at the timestamp. I think you shouldn't look at the payload format. You shouldn't look at basically you shouldn't look at anything in the RTP header. It's just basically a blob in front of the IUUP packet. And then in IUUP, you have, I think it's very close to what you see on the I'm not sure the physical layer, but maybe at the, yeah. So, I mean, in UMTS, you may know that the individual classes of bits get separate physical channels. So
I heard something about that. Oh, yeah.
We have the class 0, class 1, class 2 bits. And basically what UMTS does, it creates a transport channel bundle out of 3 transport channels, and each of those channels has a different error correction rate and encoding and so on. And in the IUUP frame, then you get those bits basically all bundled together. So you have first, let's say, a blob of class 0 bits, and then a blob of class 1 bits, and then a blob of class 2 bits. There's no multiplexing or anything that you would see in GSM where bits are spread all over the place.
Yeah.
But that's just for some background. I'm not sure if it's useful, but just sharing some of that.
Yeah, I heard something about that. But then also how, the paradigm of different frame types and not having CMR versus CMI. But I mean, either way, it's still, whether or not there is any similarity between RTP and IUUP for AMR, either way, a gateway that speaks AMR and RTP on one end and tries to do TFO AMR protocol on the other end would be just insanely complicated. Just like another way, interfacing the same RTP to an actual E1 BTS would also be messy and complicated.
Yeah, it's already extremely complex to have one leg in IUUP world and one leg in the normal GSM RTP world. And IUUP also has its own built-in signaling where basically you have a handshake process and you communicate which AMR codec rates are being used, and you negotiate different flow bundles, which are different combinations of AMR frame rates and whatnot. So there's a lot of signaling happening there as well. It's not just transporting codec frames.
Yeah.
But there's a reason we have IUUP state machines for that kind of stuff, and we only do a very, very small amount of what it can do.
Yeah.
Maybe also one comment. I mean, Niels is not here. He would have raised that for sure, since he was working on this quite extensively. You mentioned that sort of the AMR active codec set of 4 different AMR codecs in GSM. So that out of the 8 modes, you can always only have 4 of them that are active, and that this can be individually negotiated. Yes and no. The crazy part is that if you look only within, let's say, the UE, the UM interface, the ABIS, the BSC, and everything, yeah, it's all super flexible, and you can make the craziest combinations and flexibility. And then you look at how the A, specifically, I think the A. No,
I know.
That the S bits are basically reducing all those combinations to basically, well, okay, there's basically here's one.
Well, okay. Also, I think I know part of the answer. The answer is historical. Because this craziness that you're talking about on the A, that only came in with the A over IP. So basically, most of those specs were written before A over IP came along. So including all the TFO AMR specs, everything, well, really one spec, there's 28.062. So all of 28.062, including all of the complexity that it defines for AMR, for both 2G and 3G, all of that was written before the introduction of A over IP. So I still stand. Earlier, earlier, like a year ago, whatever, I made some, inflammatory statements here, which I'm still stand behind. That 3GPP screwed up royally. 3GPP screwed up bad, and I say it here on the record without shame. That 3GPP tarnished their once good reputation, because once upon a time they developed really good stuff, but when they came out with the A over IP interface, they screwed things up. So both by adopting the industry standard RTP payload formats, which are massive functional regression compared to the TRAU uplink frame format, causing all these problems that I had to fix basically by creating my own TWTSO1 and TWTSO2. So that's one area where they screwed up. But even for AMR, there they also screwed up just in a different way by doing all this thing where by having all those S bits exactly like what Niels had to work on. Yeah, and then exactly what you're talking about.